In this video, we're going to start talking about composition of functions. And composition is a different kind of operation that we haven't looked at before. And composition, the notation looks like this. It's an open circle, and you will read this as f of g of x. And what this means is rather than plugging in a number, we're actually plugging in an entire function. So this means I'm going to take the entire function g of x and plug it into the function f. And for this one here, this means I'm going to take the entire function f of x and plug it into g of x. Now, keep in mind that composition is not commutative. So what that means is that I can't change the order of f and g and assume that it's going to be the same. Just like addition is 2 plus 3, for example, is the same as 3 plus 2, I can change the order and I know the answer is still going to be the same. It's still 5. But I can't do that with composition. So composition is similar to division and subtraction, where the order does matter, right? 1 divided by 2 is not the same thing as 2 divided by 1. Just like composition, f of g of x is not necessarily the same as g of f of x. So please keep that in mind, that order definitely matters with composition. And something that always helped me when I learned this for the first time, if you notice, f here is on the left, so f should be on the left here. G is on the right, so G should be on the right here. And that's something that always helped me remember the order. If f is on the left, f is going to be on the outside when I write f of g of x. Now, don't get that open circle that represents composition confused with multiplication. Multiplication would look like this. And that would be a closed dot. That's your multiplication. Composition has the open circle. Now, domains of composition functions can be a little bit tricky. I'm going to give you the definition of how you would find it and what it means. And then I'm going to go through and show you an easy way to figure that out. So, the domain of f of g of x is all the x's in the domain of g for which g of x is in the domain of x. Now, the same thing goes for g of f of x, only you're switching your functions. So for the domain for g of f of x, it's all x's in the domain of f for which f of x is in the domain of g. So that's a mouthful, and it's a little bit hard to kind of follow, but once we go through an example, I'm going to show you an easy trick to figure out how to find the domain. Okay, first example, we're going to let g of x be x plus 3, and f of x is going to be 2x minus 5. We want to find g of f of x and f of g of x and the domain for each of them. So let's find g of f of x first. So remember, since g is on the left here, when I rewrite this, f of x is going to be inside and g is going to be on the left. So this means I'm taking f of x, let me do it in a different color for those of you who are visual learners. I'm going to take f of x and plug that whole function f of x into g everywhere I see x. So here's my red function, my f of x, and I'm going to take this whole function, which is 2x minus 5, and plug it in to this x into g. So if I were to write g is x plus 3, but I'm going to replace that x with 2x minus 5 because I'm plugging in f of x into g. So this was my x because g of x is x plus 3, but I'm plugging in f of x, which is 2x minus 5. So if I clean that up a little bit, I'm going to get 2x and then a minus 2. So there's my function g of f of x. Now to find the domain, what I want to stress, because the definition that I gave you above is a little bit tricky. The trick to finding the domain is to look at the unsimplified version. Before you simplify, look at what you can plug in for x. I can plug in anything I want for x in this case, because x is an under a square root where I have to worry about negatives under a square root, and x is not in a denominator where I have to worry about getting a 0 in the denominator. So I can plug in anything I want here. So my domain for this function, g of f of x, is going to be minus infinity to infinity. So the trick to composition is to always look at the unsimplified version to find your domain. Okay, so the second part of this problem says to find f of g of x. So now what we're doing is f is going to be on the outside because it's on the left here. So I got to put it on the left here. And I'm taking g of x. Let's do this in red. I'm taking g of x and taking the whole function g of x and plugging it into f. So my function f is 2x minus 5. But I'm putting g of x in for x. So I'm going to erase that x, and I'm going to put in x plus 3. This is my g of x, and I'm plugging it into f. So now when I clean that up and I simplify it, I'm going to get 2x plus 6, because I'm going to distribute that 2, and then a minus 5, which will give me 2x plus 1. So here's my final function, simplified, of f of g of x. Notice that these are not the same. 2x minus 2 is not the same as 2x plus 1 because g of f is not the same as f of g. Now, to find the domain, we're going to look at the unsimplified version. Here's the unsimplified version before we distributed and cleaned it up. I can plug in anything I want into that value of x because that x isn't under a square root and it's not in the denominator of a fraction where I'm concerned about getting 0 in the denominator. So my domain for f of g of x is going to be minus infinity to infinity as well. Okay, example 2, we're doing the same thing. We're finding g of f and we're finding f of g. We're doing it in both directions, and then we're going to find the domain for each one. Okay, let's see. Let's do g of f first. That means g is going to be on the left. On the outside, f of x is going to go in the middle. So that means I'm taking f of x and taking that whole function, f of x, which is the square root of x, and plugging it into g of x. So g of x is x squared. But instead of making that x squared, I'm going to plug in the whole function. F of x is equal to the square root of x. I'm plugging in the square root of x where x should be. So this whole thing is going into that x. Now if I simplify that, the square root of x squared is just x. So here's where it gets tricky. When I look at the simplified version, my first instinct is to say that my domain for just the function y equals x is all real numbers because I don't have a square root to worry about, and I don't have x in the denominator to worry about. But that's not true. if you look at the simplified version, which is what you're supposed to do, look at the unsimplified version, the unsimplified version to find the domain. I have to be careful. The unsimplified version does have a square root in it, so whatever I plug in for x has to be 0 or it has to be positive so that I don't get negatives under the square root. So my domain for g of f of x has to be from 0 to infinity. Even though it looks like it would be all real numbers if you look at the simplified version, that's not true. You want to look at the unsimplified version. The second part is doing it in the other direction. I'm going to find f of g of x. So that means f is going to be on the outside, and I'm going to take the whole function g of x and plug it into f. F is the square root of x, but instead of plugging in x, I'm plugging in the entire function of g of x, which is x squared. So now I'm plugging in x squared into f. When I simplify that, the square root of x squared is just x. Now, let's look at the domain for this. The domain, you have to look at the unsimplified version. I can plug in anything I want into this one, and here's why. If I plug in something for x, whether it's negative or positive, that squared, I do the squared first, so that squared is going to make it positive, and then I can take the square root of a positive number, or 0. So in this case, I don't have any restrictions. I can plug in anything I want, and it's because I do the x squared first, then I take the square root. So that x squared is helping turn everything that's under the x square root positive first. And then when you square root it, you don't run into any problems. Okay, example 3. We have g of x is 1 over 2x plus 1, and we have f of x is 1 over x. Let's first find g of f of x. So this means I'm going to take the entire function of f of x and plug it into g. So I'm taking this whole function, 1 over x, and I'm plugging it into that x right there. So I have 1 over 2 times 1 over x plus 1. So this one's a little tricky because I have two denominators to consider when I'm looking for domain. I have what we call the big denominator, which is this whole thing right here. That's what I call the big denominator. So that's 2 and then 1 over x plus 1. And then I have what's called the small denominator. That's what I call it, which is just, let's do this denominator right here. I have two denominators to worry about. So the big denominator cannot be equal to 0, and the small denominator cannot be equal to 0. So let's solve. So I have 2 times 1 over x is 2 over x plus 1. That cannot be equal to 0. And I'm just going to solve this for x to see what I have to be careful of. When I solve this for x, I'm going to get x cannot be equal to negative 1/2. So I have two restrictions here. X cannot be equal to negative 1/2, and x cannot be equal to 0. So when I write that for my domain, x cannot be equal to negative 1/2, so that's an open circle. X cannot be equal to 0, that cannot be 0. But it can be anything else. So when I write this down in interval notation for my final answer, I'm going to write from minus infinity up to negative a half. That's this interval right here. Then everything between negative a half and 0. And then everything greater than 0. So this is my domain in interval notation. Now, we have 1 over 2 times 1 over x plus 1. And we've got to simplify this now. So I didn't simplify it yet because I wanted to look for my domain, because we look at the unsimplified version to find the domain. And that one was a little bit tricky because we had 2 denominators to be concerned with. But now we still got to simplify it. So 2 times 1 over x is the same thing as writing it as 2 over x. And now I'm going to multiply everything by x on the top and the bottom. I can do whatever I want as long as I do it to both the top and the bottom to clear the complex fraction, because I don't want fractions within fractions. So I'm going to multiply the top by x, which gives me x, and then I'm going to multiply the bottom by x, which would give me 2 plus x. Because when I multiply this by x, right, those x's go away, and x times 1 gives me x. So this is my answer that's simplified. So this is my g of f of x. And then this is my domain written in interval notation. So let me erase, since I'm running out of room here, let me erase this. So then we can go through and do f of g now and do the other direction. Okay, so we're going to do f of g of x now. And so that means I'm going to take the entire function g of x and plug it into f. So if I take this whole function g of x, I'm going to plug it into that x. So I'm going to have 1 over 2x plus 1. So this was my g of x that I plugged in. Okay, now to look at this, I want to make sure that we'll call it, this is what I like to call it, the big denominator. That's this denominator of the whole entire fraction. This cannot be equal to 0. And then the little denominator, that's this one here, that can also not equal to 0. So this will help us figure out what the domain is. This will never be 0. 1 over 2x plus 1 can never be 0. So I don't have to worry about the big denominator. However, the little denominator, if I solve that, 2x plus 1 cannot be equal to 0. If I solve that for x, x cannot be equal to negative a half. So if I look at that on my number line, I can plug in anything I want except for negative a half. That's when I'm going to run into a problem. So I'm going to have an open circle on negative a half, and I can have anything else I want. So when I write this in interval notation, it's going to be from minus infinity up to negative a half, union negative a half to infinity. Now we have to simplify. I have 1 over 2x plus 1. I have to simplify this now. So I have a fraction over a fraction, so I'm going to flip and multiply. So I'm going to get 2x plus 1. So this is my f of g function, 2x plus 1, completely simplified. And then this is my domain for f of g. Last example before we go on to evaluating composition functions. We have g of x is equal to x squared plus 2x. and f of x is equal to the square root of x minus 1. So I have g of f of x. Let's do that one first. That means I'm going to take the entire function f of x and plug it into g. So this whole thing is going to go into this x and this x. So I have the square root of x minus 1 squared, that was x, plus 2 times x, which we're plugging in the square root of x minus 1. So this is before simplification. So my domain is going to be anything greater than or equal to 1. I can plug in anything I want as long as it's greater than 1 or equal to 1. I don't want anything less than 1 because that's when I run into a problem of getting a negative under that square root. Okay, so my domain for g of f is going to be 1 to infinity, including 1. Now let's simplify our function. If I square the square root of x minus 1, that's just x minus 1. And 2 times the square root of x minus 1 is just 2 square roots of x minus 1. So there's my simplified function, and here is my domain. For f of g of x, now we're doing it in the other direction. So I'm going to take my entire function g of x and plug it into f. So I'm going to take x squared plus 2x and plug it into the square root. And let's see, there isn't anything else that we can do with that to clean it up. However, I want to make sure what's underneath here is going to be positive. So I want x squared plus 2x minus 1 has to be positive. If I look at the graph of x squared plus 2x minus 1, it's going to look something like this. I need to find these two values right here because I want to make sure that my values are positive under that square root. So if I find these two values here, I can find these two pieces of the graph where it would remain positive above the x-axis. So I'm going to use quadratic formula for this. So you go ahead, pause it, and find your answers using the quadratic formula. Okay, once you use the quadratic formula, you're going to find that you have an x that's approximately negative 2.4. That's this one here. And you're going to find that x is approximately 0.41 for this x-intercept. So I want to make sure that I pick the values that are above the x-axis. So that would be from minus infinity up to negative 2.4, union, and then this piece right here, that second piece, of 0.41 all the way to positive infinity. So this would be my domain for f of g of x.